Hi everyone, welcome back to the Technion ECE Deep Learning course. I'm Tal, and in this tutorial we will continue our discussion on convolution, and we will build our first CNN, a convolutional neural network. And of course we will later implement it in PyTorch. But first, let's do a super quick recap of the previous lesson. So let's jump in. Here we go. So in the previous lesson, we discussed the idea that we can replace our perceptrons, our fully connected layers, with something called a kernel or a filter. And basically, we can instead of connecting all of the previous input to the consecutive layer, to consecutive neurons to the neurons in the consecutive layer, we can instead apply a filter, which is usually a small window that is going to go over the input to the image and output some features. And it's usually looking something like this. So we have an input image, and then we have a layer of filters. And the filters are usually smaller size, and the filters are outputting feature maps. So the output is also 2D, and usually as we go deeper in the network, we reduce the resolution, but we increase the channel dimension. Eventually, we will, after we are satisfied with the number of features and resolution we extracted from the input image, we will usually flatten the output and put the standard fully connected layers in order to get our output, which is usually the number of classes we are trying to classify. So the input is usually an RGB image, but so that means 3 input channels, but it can be more. So for example, we have RGB-D, so we have also a depth channel. We can also have RGB-A, where we have an alpha channel. So basically, we can have as many channels as we want. The important thing is that our input has height, width, and the channel dimension. Okay, so this is the idea that we started our discussion from, and then we moved on to discuss the basics. And the basics are, of course, how does a filter operate on an image? And it's usually a small window, you can see here, and in this case the weights of the filter are just 1. And basically we just slide a moving window over the input and multiply each input each values in the window by the filter value. So basically we just cross correlate or sum the values here, so we get the output value. And here is another example. Basically in this case the filter is this 3x3 window, and then we go over the image and perform this multiplication to get the output value. Now in this case, notice that we use our window, our filter starts from out of bounds. So basically we need to pad the input. In this case, the input is padded with zeros. And we are usually doing this to maintain the output dimension. So basically if we don't pad, then the output resolution is reduced. And let's see a more concrete animation. So in this, you can see that the input has multiple channels and it's 2D. So we have height and width. And basically in the layer we are going to pass our input through as 8 filters. Each filter is 3x3 and has the same number of channels as the input. Okay, so this is critical. Now, since we have 8 filters, the output feature map will also have 8 channels. Okay, so the number of filters determine the output of channels in the output feature map. So this is important, and as the designers of convolutional networks, we will have to keep this in mind. Okay, and we discussed we just reminded you of some basics from classification. So we discussed how we can build a classification model, and we used the softmax in order to perform classification. And we talked about the importance of feature extraction. And we also discussed that in classic computer vision, we actually have filters that have constant values that are not learned. So for example, this filter here is the derivative filter, which helps us detect edges. Okay. Finally, to sum up the classification part, we discussed the loss function, which is the cross entropy, and we analyzed what happens when our network or our model outputs values that are in line with the ground truth value, or otherwise they are mistakes. So when we output a very low probability for the correct class, then the loss function will be very large, and otherwise it will be very low. So our objective is going to be to, of course, to minimize the loss. Okay, so the basics of CNNs. So we discussed about several ideas. So the first one was that if we want to extract multiple features and we want to learn different filters, then we have to put many filters in a layer, just like we put many neurons in a layer, in a fully connected layer. And also we need to initialize them differently, because otherwise, since the learning process is deterministic, we won't learn any different filters, and we do want to learn different filters, so we need to initialize them differently, so each filter will learn something different. Another important feature or basic block of convolutional neural network is pooling. Basically, the idea is that we will perform some statistical operation, for example, the max or the mean, and basically the idea is that we will reduce the input resolution, usually by 2, and this helps us reduce the number of parameters in the consecutive layer if it's a fully connected layer, because then we need to flatten everything, and we demonstrated that it can affect the number of parameters. And the second thing it helps us is making the network more robust. We talked about rotation and things like that. Another thing which is super critical when we use convolutional layers is the stride, and basically the stride is the number of steps we take with our filter. So, for example, with the max pool, we usually take a stride of 2, so we move 2 values to the right, and usually when the stride is greater than 1, then the output resolution is decreased. Okay. And this is the idea that helps us implement downsampling. Basically, as we go deeper in the network, we want to reduce the spatial resolution. That means the height and width, but we will increase our channel dimension. So basically, for each region, we extract more features. Okay. And another thing which is, of course, related is padding. So if we don't want to downsample and we want a convolutional layer to maintain the resolution, then we need to pad. And usually padding is used for maintaining the spatial resolution. So this is also called a same resolution. So it's same. And we can also use the idea of padding for enlarge the dimensions, but this is a bit more advanced. Finally, we have the fully connected layer, right? And usually the idea is that we are going to flatten our 2D features, and then just put some fully connected layers to like we did with MLPs, and just output the number of channels. Okay, and we add this formula, right? So this formula here helps us calculate the the output dimension of convolution layer. So we will use that formula a bit later in this tutorial. But it's quite simple, and it takes into consideration the input width, right? The filter size, the padding you do, and of course the size of the stride. And we did an example here where we implemented the same convolution. And finally, we have again another example of how a filter works. So let's say we have an input of size H_in, W_in, and the number of channels or D_in. And one of the filters in the convolution layer is 3 by 3, so H and W equal 3 both. And the number of channels that this filter has is D_in. Now, this is the number of parameters actually. So basically the number of parameters is H multiplied by W multiplied by D_in. Now we are going to put the out filters. So basically the number of channels in the number of channels in the output feature map is going to be the out. So each filter creates a single channel in the output. And you can see here, for example, when you input an RGB image and you have this filter here, so this filter has 3 channels as well, and each filter creates just a single channel in the output. And you can see here that we take into consideration both RG and B. Okay, so and also, if you're wondering, we can do a separable convolution where the filters only operates on several channels and not all of them, and this is also called group convolution, and we will see how we can do this in PyTorch. But basically this is a bit more advanced, and usually the filters just take into consideration all of the channels, but it's possible to do a separable implementation. Okay, so this is the recap, and we now will learn some new stuff, right? And basically we're going to discuss some new terms and new concepts that help us train convolutional neural networks, and we of course implement everything and put everything together. So let's begin. So the first thing we need to understand is the idea of low-level and high-level features. And basically it's a rough categorization of the areas of the network. So usually when we go deeper, then as we go deeper in the network, we extract high-level features, and at the beginning we extract low-level features. So let's try to understand what this means. So the low level are the initial layers, where are the starting layers, where usually the input resolution is still high, and the filters, remember, are usually quite small, so 3x3, 5x5, 7x7. These are the usual sizes. So what do they capture? So they capture low-level features. So this is usually lines, corners, and edges. The regions that can fit inside these filters. Now, as we go deeper, so we get to the middle area of the network, then the resolution is decreased by some degree now. So basically, now regions in the input feature maps fit a larger region in the kernels, in the filters. So basically what we get now is what we call mid-level features, so usually object parts. So for example, we can get the wheel here because now the wheel area fits an entire filter. And as we go even deeper, then we extract high-level features, so larger regions of the image now fit in a single small kernel. So this is when we get when we detect all objects, like the global features. So this is the rough classification of the network areas. There are no numbers, so it's hard to say which resolution is the mid-level features, but still these are the terms that we use when we talk about CNNs. Okay, now an important ingredient, so I'm not going to dive deeper into this because we've already covered it, so it's activations, right? So similarly as we did in the MLPs, so here we activate the output feature maps, and again it works element-wise, so each cell in the 2D map is activated with our favorite activation. And to sum up this part, I'll just do a final comparison between CNNs and fully connected, though we've already covered big parts of it in the previous lesson and in the super quick recap that we just did. So when we talk about images, then fully connected networks can only do so much, because we don't assume anything. So all the pixels are connected to a single neuron, and we will need a lot of neurons in order to understand or to extract meaningful features. Okay, so the way we do this is we use something called inductive bias, and our inductive bias in this case is going to be the fact that pixels have some so the locality of pixels, right? We as humans, we understand regions in the image. So the region that shapes a wheel, and that helps us to understand the whole image, which is a car, right? So basically, when we use filters or kernels, we exploit correlation between adjacent input in the images, so the pixels, the locality of pixels, right? Now, another advantage of using CNNs for images is that usually the number of trainable parameters are lower, because filters are usually small, so 3 by 3, 5 by 5, and of course the number of parameters is also dependent on the number of channels we use, but it's usually lower than fully connected networks that reach about the same accuracy. So when you will train CNNs and you will save checkpoints of your models, the weights of the model on the disk, you will see that they usually occupy much less memory. Okay. Another important concept, which is of course relevant to standard fully connected networks and MLPs, but here we talk about it more deeply. So regularization, the idea is that we want to prevent overfitting, so we need to introduce some constraint on our network. Now, we discussed overfitting and underfitting in the recap tutorials, but in the previous lesson, we saw a phenomenon that in the MLP tutorial, we saw a phenomenon that is called deep double descent. And this is kind of deviates from the classical machine learning regime. So when we only had underfitting and overfitting, and now we have now we can actually see a second descent. But let's put it aside for now. Let's talk about overfitting in the general case, where we memorize our training data and we perform worse on the test data than if we stopped our training earlier, right? And of course, we want, eventually our target is to build models that are able to generalize. So when we deploy them in the world, they will perform they will perform good because they understand patterns and they did not memorize our training data. So, of course, to prevent overfitting, the trivial solution would be use infinite data. So if you've seen all the data in the world, then of course you will generalize because you've seen everything. But this is not practical. Well, it's practical maybe for big corporations that can train on huge corpus of data, but we are usually not capable of training these kind of models on this amount of data, so we need to introduce some constraint. And there are a couple of techniques to do so, right? And the very basic one, you've known this since the standard machine learning course. So you can just introduce some constraint over the weight. So you don't want the weights to grow too large. So you introduce some regularization, which can be L2, L1, or elastic net. And basically, this is something that we usually do in standard neural networks as well, and fully connected MLPs. And this is also called weight decay, right? But this is not what we're going to talk about today. We are going to talk about more advanced regularization techniques that really work well for images as well. So the first one is dropout, and it's not very new. Dropout is for 2014. And it's a very simple technique that works really well. And the idea is that the main motivation is an approach to approximate training a large number of neural networks with different architectures in parallel. So basically, you can think of as training an ensemble, right? And the way we do it is think about this neural network here. And during training, each neuron gets a probability P to be turned off. So basically, each time you do a forward pass, a different set of weights are turned on. So you can see here, for example, that some of the neurons are turned off, and they are not part of the output of determining the output values. Okay. Now, each iteration, we get a different set of weights. So basically, what we do here is that the effect is that we add some noise to the training process, and we actually force nodes or neurons within a layer to probabilistically take on more or less responsibility for the inputs. So if this neuron here is turned off, then this neuron has to take more responsibility, right? Now, the idea is that, so in practice, dropout behaves differently during training and during evaluation. So a training time model.train, then we do this masking. And at test time, dropout is of course turned off, and this is model.eval mode, okay, evaluation mode. And we've seen this before in the previous tutorial, but in the previous tutorial, it did nothing because we did not have a dropout layer. So this is dropout, works really well. So for filters, the idea is the same. So we will turn off some of the filters, right? So each filter has to take a bit more responsibility when we propagate gradient through it. So the idea is the same. So we will see dropout 1D and dropout 2D. So different depends on your input shape. Then you'll decide which kind of dropout to use. Now P is a hyperparameter which you need to choose and tune. So basically, typical numbers are typical percentage are 0.01, 0.05, and 0.1. Sometimes at extreme cases, 0.2 also works, but this is the range that you should tune your dropout value. Another super important technique and really cool, very simple, it's called data augmentation. And I want to motivate this discussion from an example. So in our data, we wanted to classify animals. So we have this data point here. So we have an image, and the class is of course a lion, right? Now we want in practice to have as many data points as possible. So if you want to generalize, we want to see all of the lions in the world. But of course we can do that because we will have to go and collect new data, and this can be expensive and of course usually impractical. So what we can do is, for example, we can apply some transformations. So for example, we can translate or flip the image horizontally or rotate it a bit. So notice here that we apply several transformations, and the one thing you can notice is that the subject did not change, or the label of the image did not change. These are still lions, but we increased our data by several degrees because we now have more lion images. Now, of course, it's not perfect because we can see that it is the same lion, right? But it makes the networks more robust, and of course, it can effectively increase our data size, which is always good for deep learning. And in practice, today, when we train especially classification models, data augmentation is something that we do. We always do. It always adds to the performance. Of course, you can pick really bad augmentations that will, of course, hurt the performance, but usually the simple augmentations that I'll show you now work really well. So, what kind of augmentations we can do, and how can we effectively enlarge our data set? And of course, we know that deep learning flourishes when there is a lot of data. So flipping the image horizontally or vertically, and here we need to be a bit more aware because, for example, several datasets actually can, so this kind of augmentation can actually change the label. So think about MNIST, about the one with the handwritten digits. So vertical flip can actually change the label or actually create a data point that makes no sense, right? So we need to be a bit more careful with this one. So rotation, so we can rotate the image a bit to the left, a bit to the right, so nothing too drastic. So this usually also works well. Scaling, so we can scale the image outward or inward. Cropping, so we can take just some areas of the input image. Translation, so a bit to the left, a bit to the side. Now, in every type of this transformation, we will also have to fill the missing areas. So if you translated to the left, then you need to fill the areas on the right with some values. So we usually pad with reflection or replicating the pixel values. Now, the final kind of augmentation that we can do is more general and can be applied to any kind of data, not only images. So it's very simple, just add noise. Of course, you will have to tune how much noise you add. So usually for images, when you add just a little bit of noise, then for the human eye, the image does not change at all. But as we will see later in this tutorial, actually CNNs are very sensitive to noise. And actually, if you don't train with noisy inputs, then at test time, if you add noise at test time, then you can see that it actually really affects the network's prediction. So we will see that later. So basically, you can just add a little bit of noise and train with noise. And of course, this helps the filters detect high and low level frequencies a bit better. Okay. So this is the idea of data augmentations. Now it's already implemented in torchvision, and it's kind of really a good practice to use data augmentations, and everybody's doing it. And because it has become very popular, there are now alternatives to perform augmentations in order to make these operations faster. So basically, this can cost us with time complexity, right? Because we take each image and we apply some transformation on it. So this costs time. So here comes Kornia. And Kornia is a PyTorch-based library, which is a differentiable GPU-accelerated augmentations. And the idea is that instead of performing this augmentation on a single image, we can perform it on a batch of images, and we can also perform these transformations on the GPU. So in torchvision, the augmentations are usually performed on the CPU. Okay. And we can't do this on the GPU because it's not implemented like this. But Kornia does allow us to do this on the GPU, and it's very simple. The API is very similar to torchvision, and you can see here the benchmark. So basically, for when you operate on batch, then the augmentations are performed much faster. So we can train a lot faster. And of course, since we already operate on tensors, then some of the augmentations are differentiable, which is nice because we can propagate gradient through transformations, which can also help us sometimes with accuracy, or when you want to implement an augmentation, like not in the beginning, but in later parts of the network. So they do not serve as a gradient block, right? So use Kornia if you want to utilize a heavy use of augmentation, then Kornia is the way to go. So what we are going to do now is we are going to implement a CNN, convolutional neural networks, and it's a good time to introduce some image datasets. Now, I'll mention that in practice we have a lot of datasets already implemented in torchvision, and we can just call them, and PyTorch will automatically download the data to our disk. Now, in many cases, you just want to fine-tune maybe on your own data, or you have data that you collected yourself. So we also have functions for that. So basically, you can take a look here at the image folder and vision dataset. So basically, these two classes can help you implement an image dataset on your own. But for our purposes, we can easily utilize what torchvision already has for us. And the first dataset we will meet is the ECE046211 dataset, which is a very popular dataset. And it consists of 60,000 32 by 32 color images in 10 classes with 6,000 images per class. And we use 50,000 for training and 10,000 for testing. And of course, when you train a neural network, you should take some portion of the training data to be your validation data. And the classes are completely mutually exclusive. There is no overlap, and you can see examples here. Now the ECE046211 dataset is considered kind of hard because even for humans at this small resolution, it's quite hard. So I wouldn't, for example, it's not easy to see that this image here is a bird, right? And this is why it's hard, but we can apply neural networks on it and perform and get to really nice accuracies. So let's do that in practice. Now, there are several parts. So the first part is the pre-processing and the augmentations part. So what transformation are we applying on our data? So we begin with an example with torchvision, and next we have an example with Kornia. So you can pick which one you like, but for faster training, use Kornia. Okay, so we define the sequence of transformation we want to apply on the training data and on the test data. Now, here we are performing random crop, random horizontal flip, and these transformations, right, they are applied on something called a PIL image, PIL image. And a PIL image is just the standard data class for images in Python, okay? And the idea is that the input is just uint8 values, so between 0 and 255, okay? And PIL image is the standard way to represent images in Python. And these transformations are operating on a PIL image. So pay attention, they do not operate on tensors. The next thing we do is we take this uint8 image and transform it to tensor. And what this line here is doing is it is transforming your uint8 values to float tensor between 0 and 1. So it takes care of normalization as well. So keep that in mind. And the final thing we do is normalizing. And what we do here is standardization. Basically, instead of working with values between 0 and 1, we work with standardized values. So here is the mean and here is the standard deviation. And this is a channel-wise mean and standardization. So basically, this is the mean value of the red channel, the green channel, and the blue channel, and this is the standard deviation of the red, green, and blue channel. Okay. Now, how do you calculate these values? So basically, you need to you need to iterate over your entire train set. You need to save your R and G and B values for all the images, and then you just calculate the mean and standard deviation, right? So you will see this a lot. It's not mandatory, right? You can just remove this and work with values between 0 and 1, or you can even normalize between -1 and 1. Everything works. Just take what works better. And standardization is something that we did also with classical dataset. So the idea also works for images. Okay. So just do whatever works best. But here we show you an example of standardization. Now, for the test set, we only care about classifying it correctly, so we don't care about augmentation. So we just transform it to tensor, and we perform the normalization that we did for the train set, because this is the value range that the network is familiar with. Now, I'll just mention that there is something called test time augmentation, TTA. And the idea is that for a more robust prediction, we can, so let's say we have trained our network, and preferably we trained it with augmentations. Then at test time, we get an image, and we want to get the best prediction we can. So what we do is we take this image and we apply some augmentations to it. So for example, from one image we apply 5 augmentations, so we end up with 6 images, and then we forward these 6 images through our train network, and for each augmentation we get the score, we get the probability, and we now can average the probabilities and take the class that got the highest score, right? So this is just help us to make the network more robust. So this is just an idea that is called TTA. So we can call PyTorch, we can get cifr10 easily from PyTorch, and we can tell it to download. So don't worry, if it's already on your disk, it won't download it again. It will just print file already downloaded and verify. Okay. Now we have the train portion of the data and the test portion of the data, and I'm not doing this here, but you should further separate it to train and validation. Okay. Okay. Now, just to see the effect of the augmentations, what I'm doing here is taking a batch of images, and you can see here what are the augmentations that we called here are doing, right? So you can see the translation and the cropping and everything. Now I'll just mention that these are random, so basically you can also initialize them with probability of your choosing, and there are several default values here that we use, but you can change it according to your liking, and of course this can be tuned, and should be tuned if you have the resources to do it. Okay. So this is what we do in torchvision. So basically the idea is that we load an image from the disk, we apply an augmentation on it on the CPU, and then after that we will transfer it to the GPU when we train it. But we can do something else. We can do this with kornia, And for kornia, our only transformation will be to tensor, or you can also add a normalization if you wish. But this is the torchvision transformation. And in kornia, you apply your augmentations on the batch. So basically, in the training loop, you just apply this augmentation list. Okay, and we have many kinds of augmentations, and this is faster for working on batches. So basically, here we created our dataset and passed it the transformations that we want. These transformations are happening on the CPU. And if you want to use kornia, then you'll just use this. You just transform your pill images to tensors, and then during training, when you get a batch, you apply this augmentation list. Okay, so this is the idea. So let's build a classifier with PyTorch. And we are not going to, so this is just an illustration, but this is not exactly what we are going to build. So what we'll have here is just an example of how many parameters and how the convolution works. So we're going to have CFR10 images. So the images are 32 by 32, and they have 3 channels RGB. In this example, we have layers of 4 filters of size 5 by 5, and each filter has 3 channels because the input image has 3 channels. Okay, when we convolve the filter with the image and we don't pad here, then we get 28 by 28 by 4. So we have four channels in the output because we had 4 filters, and the output dimension is 28 by 28 because we did not pad. And for 5 by 5, using the convolution formula, we get 28 by 28. And we continue doing so until we reach some lower dimension that we can pass through a fully connected or something for classification. Now, this is the basic idea. This is not exactly what we're going to implement. We are going to implement something much deeper, but keep in mind that the idea is the same. So here we have our convolutional network, or CNN, and notice that it inherits from an nn.module, just like all the previous models. We have the init and the forward. Okay, in the init method, we define our building blocks. So we will have our conv blocks, and we will have our fully connected blocks. And then we just build our, here we define it with nn.sequential. So basically we'll define the order of the filters before the forward. So what happens here? So we get our input, right? And the first convolutional layer is 3 for the input channels, right? Because RGB. And then we are going to output 32 channels. So this means that we will have 32 filters, and we will use kernel size of 3 and padding of 1. Now, for this case, for kernel of 3 and padding of 1, according to the convolution formula, this is convolution type same, because the output dimension are not going to change when we use this kind of a combination of kernel size and padding, right? And from PyTorch 1.13, I think, you can just use padding equals same and not 1. But it's a good practice to understand the sizes. So basically, I recommend just continue using the numbers. Now, you can see here, this table here is how we implement the same convolution, right? So for a kernel size of 3, padding of 1 will result in the same convolution, 5, 2, 7, 3. So 7 by 7 kernel, then the padding of 3 will result in the same convolution. And so basically the resolution here does not change, okay? And then we have another convolution layer with same convolution, and eventually we end this block with a max pool. So basically the input resolution is reduced by 2. So from 32 by 32, we get 16. And we have another block and another block. And finally, we have the fully connected layer where our input is flattened. So I'll show you how to calculate this. So basically, the output feature map is of size 4 by 4 with 256 channels. And when we flatten it, it's just 96. And of course, we also have normalization here. We will talk about normalization later in the course. So for now, just take it for granted. And we also have dropout. Okay, so you can see dropout 2D here, where the hyperparameter is 0.05, the probability to be turned off. So each neuron has a 5% probability, 5% chance in each iteration to be turned off. And we also have dropout 1D here. So here it's 10%. So how did I find these numbers? So it's just hyperparameter tuning. These are typical values, but they also worked well. So maybe let's jump to the board just to make this a bit more analytically. So we said, so our input is 3 channels and 32 by 32, and we said that when you use kernel size of 3 and padding of 1, this is the same convolution. So basically, the spatial resolution is maintained until the max pool 2D. So here the output channels are 64. So basically the output dimension of this block is 64. So we have 64 channels, and the spatial resolution is 16 by 16 because we had the max pool here. So from 32 we went to 16 by 16. We have another block here, 2 conv layers, and the output channels are at 128. And we also have another max pool. So from 16 to 16 we go to 8 by 8. The final block again, so we have 256 and 4 by 4 because we had this max pool here. Now what we're going to do, so we have an image where the size is 4 and 4 for the height and width, and we also have 256 channels. What we're going to do now is flatten it, and when we flatten it, it's just the multiplication of all the values. So this is 496, and this is why this is the number of the first linear layer. And now we have the fully connected layers until we get to the output layer, which outputs the number of classes, so 10 for C410. Okay, I hope this is clear. In the forward pass, you can see that it's very simple. Just take your image, output the convolutional part, flatten, and basically you can also use nn.flatten in the init block if you want to just want to do the flattening here. But here we just do it for clarity. And finally, we get our prediction. Okay, cool. So we've just seen the basic parameters of a convolutional neural network, but there are many more, and you should get familiar with them. And so, for example, in general, these are all the hyperparameters. So the bias, we know, it's just like in fully connected neural networks. So we add the bias. We also have dilation and the stride and the padding and the padding mode. Okay, so dilation, it controls the spacing between the kernel points, and basically when we want to enlarge the resolution, we use dilated convolution. And this link here will lead you to a visualization of all the types of padding and padding and dilation and all this stuff. So it's really nice. So you can see the effect of dilation. And groups. So we talked about that we instead of operating on the entire channels in dimension and on the entire channels for each filter, you can do a separable implementation. And this is also called group convolution. So the default is group 1. So each filter operates on the entire input channels, but you can also have groups now equals number in channels. So this means that each input channel is convolved with its own set of filters, right? And this is also called sometimes depth-wise convolution. Finally, you can have the general case of group convolution, and basically this is how you implement it. We also have the padding mode. So basically the default one is 0, so just padding with zeros outside the regions, but you can also reflect, replicate, or circular. So this costs a bit more computationally, okay, but sometimes they can lead to better performance. Now for PyTorch 1.13, you can replace the padding with numbers with just string, and just like in MATLAB, if you're familiar with, you can use valid, same, and all this kind of stuff. Okay, now we did this computation of the channels rigorously by hand, but you don't have to do it. You can actually draw as many convolution layers as you want, and you can just automatically calculate the output. So for example, here we just initialize dummy input, okay, of the sizes of the images we intend to train our network on, and then we can just take this dummy input and forward it through the convolutional layer and just print the shape, okay. And then you can see that when we flatten the output, we just get the number that we calculated by hand. So this is nice. We can also use this line here to see how many parameters there are in our network. So in this network, we have around very close to 6 million parameters. So maybe sounds like a lot, but today we are talking about billion parameters and trillion parameters for the very large models. We can also calculate the size of the network on our disk. So in this case, this model is going to occupy around 20 megabytes. Okay. Now it's time to train our model, right? And not surprisingly, the training loop is going to be very much like the previous thing we did, except that we work with images. So we will define our hyperparameters. We'll load our training data. We'll define a device, criterion, cross entropy in our case. Now, just know that we did not, in our network, there was no softmax layer because cross entropy, when you use the nn.cross entropy loss, it accepts logit, so the unnormalized scores, so it applies softmax for you, so no need to do this manually. Since we hard-coded everything, so there are no input parameters for the C4CNN, but it's a good practice to do this like a more more robust and just use parameters and not hard-coded numbers. And of course, we transfer it to device. We define our optimizer, and then you have a function to calculate the accuracy. Note that we use model.eval because we have dropout and batch norm, and dropout and batch norm behave differently at train time and at test time. Okay. Now, this accuracy function will also return a confusion matrix, which we will see what it is soon. So our training loop looks very much the same that we did before. So model.train to activate dropout and batch norm, and or activate dropout and batch norm just it still works, but behaves differently. We'll talk about it in the coming lesson. We take the data from our batch, labels and inputs, transfer them to the device, forward pass, loss, and the 3 regulars, 0 GWT backward step, everything the same. Network trains, we can calculate the accuracy as we go. And of course, you should do this on the validation set and not like on the test set like I do here. So keep that in mind. So training accuracy goes up, training test accuracy also goes up. Make sure to not overfit. Now, the one thing that is new here that I show you is that we save checkpoints. So basically, we save the checkpoint every 20 epochs, but basically you can define the parameters for when you want to save. So if you have the best accuracy, then save the model, or if you reach certain time, then save your checkpoint. Whatever works for you. It's very simple. So just save torch.save will save the checkpoint on the disk. Okay. Now here is an example of how to reload the checkpoint. Also very simple. Okay. Now we calculate our accuracy on the test data, and we also calculate the confusion matrix. So our test accuracy is 84%, but we also plot the confusion matrix, which tell us where the model is confused. So basically, we can see that, of course, so the y-axis is the actual class, and the x-axis is the predicted category. So we can see, of course, the ideal cases where the diagonal is super dark. That means that we are right on everything. But you can see that sometimes for cat, the model classifies them as dogs. And this helps us understand what are the weaknesses of the model. Okay, and it's important because maybe we can do something differently with our augmentations, maybe more layers, less layers, things like that. So this helps us to understand how we can improve our model in the future or in the next iterations of our training. Nice. So we are done training our model. Now we can actually try to understand what the model is learning. So we have this nice demo here. And basically what you can see here is a classification network, a convolutional one. And here we have the image of a car, and we are now passing it through the network. And we can actually take a look at the activations and what actually the convolution is doing, right? So you can see how the filters operate to create the output feature map. And we can see that initially we get the low level features, right? So basically what we get here is just the activation. So you can see just edges and corners and things like that. And as we go deeper, we get more global features because the resolution goes down, and a bigger part of the inputs fits in a single kernel, right? So we can see global outputs. And finally, the output is determined by flattening the feature maps. You can see the effect of max pool. and basically we can see which activation contributed the most for our final classification, which is using softmax. And we can also do this in code. Okay, so basically we can visualize a couple of things. So as you recall, the filters themselves are also 2D, so we can plot them, right? And basically in our network, in our C4 network, the first layer has 32 kernels, 32 filters, right? And each filter is 3 by 3 and has 3 channels because the input is 3 channels. So we can actually plot the filters. So it probably does not mean much, but it may be nice to see that every filter learns something different. Okay. We can also what we can also do is take a pre-trained model. We'll talk about pre-trained models later in the course. But for the sake of this demonstration, we will take a pre-trained model, a larger network that was trained on many classes, and we'll take this image of a kitten. And what we are going to see is we are going to plot several stuff. So the first thing we are going to do is take a look at the output of each layer. So in this case, the network is VGG16. Don't worry about all these lines of code. We will talk about them when we'll talk about transfer learning, where we will load pre-trained models and we can use them in other tasks. So don't worry about that for now. So let's see, we can take a look at the output of each layer. So basically what we can do is see what kind of features are learned in each layer. So we can see that as we go down in the network, more global features are detected. So basically here we can actually take the shape of a cat, where here we focus on the eyes, maybe the nose, maybe the pointy ears, and things like that. So this is nice. What we can also do is we can actually pick a certain layer and visualize the output of each filter. So we want to see what kind of feature each filter learns. So you can see here that in a single layer, each filter learns something different. Okay, so this is also nice because this is what we want. We want to extract different features from our input, and more filters is potentially can lead to learn more features. So this is a nice visualization to understand what our model has learned. And of course, it can help you debug in case there are problems with your train. Now, to finish this tutorial, we'll talk about the problems of convolutional neural networks. And there are several. They work really good. And though the idea is quite old, they are still widely used. And especially if you don't have like a very large amount of data, and the TNNs work also on smaller amounts of data. So the first problem is the sensitivity to adversarial text. So this is what I tried to tell you earlier. So let's say you trained your network without any augmentations, and now at test time you take this image of a pig and you add a very small noise. Now, the image for the human eye does not change. You can clearly see this is the same pig. However, when you propagate it through the trained network, which was able to predict with high accuracy that this is a pig, it now predicts, after you added the noise, it now predicts it as an airliner, like a big plane. And of course, this is wrong, and this is what is called adversarial tech. Now, the way to reduce this or to alleviate this is basically just to add noise during training. Now, how much noise and how many levels of noise, of course, is something that you should tune, because it can also hurt the performance on clean images. So in order to make the network more robust, there is still work that you should do in order to make the network more robust. Another problem is that sometimes in classification, when we usually classify images where the subject is in the center of the image, then sometimes the network, the CNN, takes the background as a strong signal to identify the subject. So, example, if you it's commonly in the data you have images of cows, and cows are commonly are placed on a green background in the meadows, right? And at test time, you give the model a cow which is on the beach, and the network has learned to correlate green backgrounds with cow, and now you have a cow on the beach, and it does not recognize that there is a cow here because there is no green background. So this is also a problem, and the way to alleviate this is usually also augmentations, where we change the brightness and the colors of the input image, just like slightly. But of course, it's kind of hard. Finally, we have the problem of exhibiting undesirable biases, and the problem here is a bit more serious than the others, in my opinion. And for example, what you can see here is that this image here has 73% probability to be a ping pong ball, and this has 15% of being a basketball. And of course, this is weird and undesirable, and the reasons for this are usually unclear. And who do we blame? Do we blame the model or do we blame the data? Is the data unbalanced, or is the model trained or overfitted to several specific cases? And one hypothesis is that despite the balanced distribution of races in pictures labeled basketball, black persons are more represented in this class in comparison to the other classes. So basically, in football, there are less black people, for example. I'm not sure if that's the right case, but you can read about it a bit more here. And of course, we want to eliminate that. And the way to eliminate it is considering all these kind of ethics problems when we want to deploy our models. And we need to make sure that our models are balanced, and of course that the data is balanced. So it's quite hard pointing a finger who's to blame here, but it's still something that we should think about. Okay, and we talked about the applications in the previous lesson, and that's it for this tutorial. Thank you for watching, and I will see you next time.